Thank you for the kind introduction. Good afternoon, everybody. Today I'm going to present generation physical informed and accurate training data through XCT simulation for the deep learning applications. So I'm going to start with my talk, short introduction with XCT and CT simulations, then continue on what is our main goal and explain our research correction. Then after I will show the methods and results we achieved, and I'm going to finish my talk with the conclusion and future goals. So if we start with the short motivation, it's already some people explain what's the importance in XCT. Also the numerical simulation already explained how we can integrate in our research. So XCT is one of the most powerful imaging techniques still in NDT to analyze porosity, also defect detection. It's also additionally important for the safety regulations, also the quality check of the specimen to ensure quality of the image. However, detecting defects in X-ray imaging still challenging problem, especially in the small defect type. To detect this kind of defects, so we need to optimize parameters in the CT scans. Then this process can be sometimes quite time-consuming, also hard process. To optimize this process, instead of using like a CT device, we can also apply the numerical simulations. We have also our in-house simulation tools. It called SimCity. This tool can be used for artificial defects such as pores, crack, inclusion. It can be inserted in the specimen, and we can create like a realistic simulation. It can be used also like a comparison for the physical effects, uncertainty-related cases. It's kind of replacing the real scan and creating like a realistic image as in like specific CT devices. This is like a quite important to save time and energy. So in our simulation tool, we have like several X-ray sources and detectors. You can see like a two of the example. One of the ray scan 250, and the other one is Yosifov. So basically, we are taking all of the information from this device, integrating them our simulation tool, then creating the realistic image. As you can see here, like one example from the simulation, the other one from the ray scan CT devices. Additionally, its working principle of the simulation tool is starting with tracing of the specimen, then calculating the spectrum with Lombard-Beers law, and optionally we can add like different physical effects here, such as object and detector scattering, and geometric blurriness effects, and image noising. So our motivation is like how we can integrate these XCT simulations and convolutional neural networks to increase the defect detection size. So we define like several questions to answer, and we use like a different kind of methods to achieve these goals. So first of all, we created like simulations with and without physical effects. What is mean physical effects in that case? We can simulate like a focal Gaussian blurriness effect and detector modular transfer function and noise in photon and Gaussian noise to create our training data. So the second step, we converted the STL files directly to binary volumetric mask to use this mask as a training mask in the training process. We also applied like a CT simulation and real data combination to train the neural networks. Still this process in progress. Will not show today, but yeah, in the future work we are working on that part also. For the detection method, we have used like a UNet, VNet, and modified 3D UNet. Modified 3D UNet is implemented by us. It's basically modification of the UNet in 3D we were adding like additional convolutional layers and error layers in the decoder stage to increase the image quality in CT. To compare our image, we applied like three methods. The first one is structured similarity index. The second one is the probability of defect detection. So you see here like one example image from the probability of defect detection. So the red line shows here like a POD curve, and blue and green dashed line show the confidence bounds at 95%. A90 means like a probability at 90% and A90, 95 with the confidence bounds. So after A90, what we learned from this POD curves, after A90, 95, all of the defects has to be detected with the probability 90% plus with the confidence level 95. In our previous study, we applied also similarly like same convolutional neural networks here. For the training data, especially the training mask, to creation of the training mask, we applied auto threshold and manual segmentation with the cleaned data. So it has been compared also like a traditional methods also with the convolutional neural networks. So we find out like a convolutional neural networks is performing so much better than traditional methods in the segmentation task. You can see also one example of the simulated defects here. We were defining like a 6 different type of defects with different material type, with different shape, also in the different location. So this is the cutout defects from the full specimen, and we were training this fully informed data in the neural network instead of like missing a lot of like unknown place. We know where is the defects exactly, we know the full characteristic of the defects, then we can also measure the performance or also the algorithms. So this was the previous result on segmentation mask is overlying on the real simulations. So we can see the prediction on the right hand side and ground truth we created on the left hand side. So we were able to increase our segmentation result with our modified 3D unit algorithm. So if we look at the first and the last image, it was we were able to segment like a really small type of defects. The size is about 4 cubic millimeters in that case. If we check also the shape analysis of the defects, you can see here like some of the defects has been segmented really good shape with the accuracy, let's say 95%, but still there was some potential improvement in that case. So that's why we change our training mask. So we define like two different methods to use them in as a training labels. Firstly, we create the STL object, then convert it directly from the STL to binary volume. And the second method is we remove all of the physical effects from the simulation, then create the simulation with and without physical effects. So you can see like one example, we don't have any noise, we don't have any balloonist effect. Of course, it's easier to segment this kind of defects or objects. However, I should also mention the conversion between STL and binary volumetric tests. It's only working now for the basic shapes like spheres, cylinders, and if we apply like a complex shape, it is quite performing not so good, I can say. So this is the training and testing principles. Firstly, we started with the defects without any physical effects, and we create like like 3 different shape here. One of is cone, one of them is sphere, one of them is cylinder. Without physical effects and with physical effects. Then we create the mask with without physical effects in the left-hand side. Then use this mask with the noisy data to train the neural network. In the next step, we applied the model, we create the model, then this model applied on the unseen defects. So we were not training the defects in the training set, we applied unseen ones. To how we can measure the performance, then we applied the probability of detection, also the dice coefficient, basically checking each voxel similarity between 2 binary masks. How did we optimize the projection numbers also? Without any physical effects and with physical effects, optimization done by one CT scan, real CT scan. Then we were creating like a similarly with simulations. Then we measure the structure similarity index between these. So without projection, you can see like here, it's like with 800 projections, it was reaching like almost similar case with 1200. That's why we use to segment these projection numbers 800 without physical effects. With physical effects, we applied 400 projections as we created the CT image with 400 projections. So this is the first result we achieved. In the previous results, we were only able to segment like a 64 of the defects. Now 3 of the convolutional methods able to segment 100 of them. You can see also the defects on the right hand side in the CT images. And the voxel size starts from 50 micromillimeters to 1.1 millimeters in this case. Again, we applied the same model, this time like extremely noisy data, but we know we define these defects and we know all of the characteristics about the defects. So when we add the noise, actually, in some case, visually it's impossible to distinguish if there's a defect or not. But trained algorithm was able to actually segment really small one, especially like that one, and yeah, most of them was performing good. But of course, there are some issues. In the first one, we had some artifacts for the segmentation, but visually also it's impossible to ensure that there's a defect. Again, we applied the same data. We were able to increase the detected defect number like at least 10 for each of the algorithms. Also, the accuracy was quite high. Then we compare we compare them with the probability of defect detection to check the minimum detectable region. And if we use the training tables auto threshold, you can see the results for 3 cases. Blue dashed line is the modified 3D unit. Black one is the UNET, and the red color shows the VNet experiment performance here. So both of the methods we achieve to increase minimum detectable region to create with creation of the accurate ground truth. But still, there are some potential to increase this detectable region because we only use like a specific or known geometries for the training data. We haven't used any like a complex shapes in the training data. If we add also these complex shapes in the training data, then we can still increase the detection. To conclude everything, like we were defining 2 different ground truth generation methods. Then both methods achieve like increasement detectability for small defects. We also tested like with different noise level and different projection number. And in the final, we measure the performance of the method with the convolutional neural networks with probability of defect detection and dice coefficient similarity. To conclude, both methods has increased, again, detected defect numbers. POD results indicate the improvement on the minimum detectability. It shows we can use like a combination convolutional neural networks and the CT simulations to train neural networks, then apply this model also in the real data set. Overall, it has a potential of the both of the method, but still we have to increase the accuracy of the labels. Next step, we are planning to create like a also accurate binary volumetric mask and complex shapes, and create a model, apply in the real data sets, and extend this process for example, carbon fibers, aluminum alloy, and other kind of material. So this was it. Thank you very much for listening. If you have any questions.